Well, hello there, team. Chemistry Coach coming back after a very short video prior to this on the intro to colligative properties. Let's start looking at laying the foundation for when we're going to get these equations for vapor pressure lowering, freezing point depression, boiling point elevation, and osmosis. Specifically, we're going to attack osmotic pressure. Well, and again, we'll do videos of each of those separately. But we have to account for the type of solute. And this caused some problems back in the late 1800s, because colligative properties, remember, depend on the number of solute particles, not their identity. These are specific types of properties that depend on this physical interference of these solute particles with the solvent, and it alters the properties. Well, back in the day, a lot of chemists weren't really aware of the difference in these solutes as we know now: strong, weak, and non-electrolytes. Right? So we're going to have to do, I highly recommend you review the video on electrolytes. Right? That's from first semester of general chemistry if you're a little weak on that, or a little rusty dusty, you don't remember much. So we'll review that a little bit on the next board there. But remember, you've got non-electrolytes that do not dissociate or ionize in solution. So when they go in, like a sugar or something, 1 molecule of sugar in the solid phase is 1 molecule of sugar in the aqueous phase. It's a 1-to-1 ratio. But you take a strong electrolyte like a sodium chloride, a soluble ionic compound, well, that 1 mole of sodium chloride becomes 1 mole of sodium ions and 1 mole of chloride ions. So it actually forms 2 moles of solute particles. Oh no! That's going to screw things up, right? So what happened is people studying some of these properties would expect this value and measure this value. It'd be almost like, for sodium chloride, like twice as impactful as they thought. Or if it was magnesium chloride, which would form 3 particles, the expected effect would be 3 times higher than they anticipated. They're like, what's going on? Right? They didn't really understand the electrolyte effect until later with Svante Arrhenius explaining that, which we'll do on the next board. But Jacobus van Hoff was looking at a lot. I mean, this person did a lot. I mean, one of the grandpapas of physical chemistry, huge in organic chemistry. One of those people who had their finger in like almost every chemical kinetics, equilibrium. And you think of something in chemistry, Jacobus van Hoff probably had a particular impact on it back in the mid to late 1800s. Actually got the first Nobel Prize. I think he got the very first Nobel Prize in chemistry, if I recollect, 1901, something like that. So he may, don't quote me on it. You might want to double check that. But I think Jacobus van Hoff was the very first person not to win a Nobel Prize, but to win a Nobel Prize in chemistry. So impactful. You'll hear that name pop up later if you haven't heard it before already. But when Jacobus van Hoff was looking at some of these colligative properties, vapor pressure lowering, freezing point depression, boiling point elevation, they were kind of looking at everything as being a non-electrolyte, right? 1 particle becomes 1 particle, right? So this 1-to-1 ratio. But he was measuring values of colligative properties that were different from what he expected. And he's like, what is going on, right? Especially for strong electrolytes. And so he came up with this Van Hoff factor. Didn't mean he could explain it at the time. The little letter I, right? And what I'm gonna do is I'm gonna take these equations that we use for some of these later videos, boiling, an equation for measuring the amount of boiling point elevation or the amount of freezing point depression or osmotic pressure. We're gonna put a little fudge. It's not really a fudge factor, but a little factor to account for the type of electrolyte. If you've got a strong or weak electrolyte, you're gonna have to account for the fact that that is going to dissociate or ionize in water to produce more solute particles than you had anticipated if it was a non-electrolyte. Haha! Like, thanks Svante Arrhenius for that one. And it's even worse than we think with ion pairing and whatnot. I'll talk about. So this little letter I accounts for the type of electrolyte. Okay. And so what Svante Arrhenius put that as, it was the value he measured in a laboratory, divided whatever the value was, boiling point elevation, vapor pressure lowering, doesn't matter, and divided it by the expected value. Okay, so this is what he expected, that's what he measured. So a lot of it would be, he'd get values close to 2, close to 3, like sodium chloride would be really close to 2. He'd be like, what's going on? So let's look on the next board and review a little bit of non-weak and strong electrolytes based on what Svante Arrhenius did. Should be a review from first semester general chemistry or prep chemistry, because that's going to help us determine what the value I is. Okay, so if we want to, and this is something I expect you to be able to do in these types of problems when I have you determine some colligative properties for solutions. And again, I'll provide you the equations, but I want you to be able to figure out what the Van Hoff factor is, that little I, which accounts for the type of solute in there. Is the solute a non-electrolyte, a weak electrolyte, or a strong electrolyte? You're going to have to identify that. And then based on Svante Arrhenius's theories on electrolytes, right, electrolytic dissociation, so we know, strong acids and weak acids ionize in water, soluble ionic compounds dissociate in water. We'll talk about weak versus strong. Let's focus on non-electrolytes first, but I would expect you on my homeworks, quizzes, and exams to be able to use Svante Arrhenius's concepts on electrolytes to estimate. Right? It's not perfect. Commonly, we would call the Van Hoff factor an exact value, but it's really not, because there's worse things happening in solution that we don't even, well, we know about, but we haven't taught you about yet. So we're going to be estimating values for I, the Van Hoff factor. If it cannot be estimated, I will provide you a value for that. We can even calculate for it too, but I'll show you how to do that later. Let's look at the three different types of solutes. So non-electrolytes, we'll start with those. Those are the easiest. And then we'll do strong electrolytes, and then we'll do weak electrolytes. So non-electrolytes, if you remember, right, review that video on electrolytes. They do not, if you add that solute to water, we're going to focus on water as our solvent right now. So if you add that in there, it can dissolve, but it's not going to dissociate. It's not like sodium chloride, like an ionic compound that breaks apart into cation anions, right? So that's not going to happen. And it won't react with water like a strong acid might, right? So it won't ionize in water, it won't dissociate in water, but it could dissolve. For example, let's take, I think it's sucrose or something. So let's take the solid, you take sugar, boom, add it to water, and it just physically dissolves, right? Doesn't react with water. So one molecule of sugar in the solid phase forms one molecule of sugar in the aqueous phase as a solution, right? Or 1 mole of this produces 1 mole of that. So it's the same number of particles. So if we're looking at colligative properties, which depends on the number of solute particles, well, it's pretty easy to say the number of solute particles in solution is the same as the original number, and we'll be talking usually in moles. Therefore, if that's the case, let's do our therefore signal. The Van Hoff factor is always equal to exactly 1, and we'll call that exact in my class. Typically, when colligative properties are taught, it's always based on the assumption that the solute is a non-electrolyte. And that's kind of what Jacobus Van Hoff was doing at the time, even though, like I said, Svante Arrhenius hadn't explained electrolytes and stuff yet. So he was always, he didn't even use the value of I, but he found a lot of solutes, sugars, organic compounds, things like that, would provide colligative measured values that match what he expected. Well, that's because I equaled 1. He wasn't thinking that way. Oh, I equals 1. The I is going to come from, we're going to look at I this way through Svante Arrhenius's point of view. Right? Remember, Jacobus Van Hoff was looking at I as a ratio of the measured over the expected value of that colligative property. But now we can estimate it just looking at electrolytes, which we understand now. Hopefully so. So for all you need to know, if it's a non-electrolyte, it does not dissociate or ionize in water, and it produces the same number of particles as it started with before it was in solution. Boom! I equals 1. Yay, those are easy. Now, for weak and strong electrolytes, obviously I is going to be greater than 1, right? Because it's going to be forming more particles. Let's look at strong electrolytes. Remember strong electrolytes, my friends? And again, if you're not 100%, confident in this, review the electrolyte video. Please, 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 I beg of you. Learn. So these are electrolytes. These are solutes that, when placed in water, will either break apart, like a soluble ionic salt, right? Sodium chloride, those kinds of things. Or ionize, which means it's going to react with water. These would be your strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, right? Remember those? I don't know if I got them all there, but I got a chunk of them. So they either break apart in water or react with water to 100% extent, forming ions, right? That's why they conduct currents, make the light bulb glow or the LED blink in lab. Remember some of those little labs we did? For example, let's take a soluble ionic salt or compound, right? And you can either draw this as AQ splitting apart or as a solid dissolving in water and forming, separating the cations from the anions, right? To make life simple, we're just going to make the assumption this is happening to 100% extent. But technically, in reality, we're going to have some issues. And I'm depending how I feel, I may mention this in the last minute or so on this video, that we don't quite get these perfect exact values of I, which, all right, but I might save that for a later date. But would you agree that in barium nitrate, we have 1 mole of barium ions for every 2 moles of nitrate anions, right? It's a 2-to-1 ratio because nitrate's -1 charge, barium's a +2 charge. When that breaks or apart or dissociates in water, you'll get that 1, remember the subscript here becomes the coefficient there, you get 1 mole. So 1 mole of barium nitrate would form 1 mole of barium ions with a +2 charge. And remember those spheres of water molecules around them we talked about? And you get 2 moles of nitrate ions. So in solution, you're going to have 2 nitrate ions floating around for every 1 barium ion in a 2-to-1 ratio. Maintains the electrical balance. But would you agree, 1 mole of barium nitrate, when it dissolves, forms 1, 2, 3 moles of ions. And since colligative properties depend on the number of particles, that's 3 times more particles than Van Hoff anticipated. So his measured value of the colligative property over the expected value would be in the range of 3. And he's like, what's going on? Right? So for this class, for that strong electrolyte, I would be 3. So we're going to pop that value of I in these equations I'm going to derive for you later in some of the next 4 videos. And you would pop, if the solute is an electrolyte, a strong electrolyte, for the value of I, you can do this in your head or you can do it on paper, I don't care. But you have to be able to see this dissociation process for soluble ionic compounds in your head and be able to determine how many cations and anions are formed given 1 mole of this. And that will be I. And that'll be a unitless number in this case. Now for strong acids, right, let's take hydrobromic acid for an example. That actually reacts with water, right? So donates the H+, so you get the hydronium ion, right? And then you get the bromide ion. You get the conjugate acid and the conjugate base over there. Well, 1 mole of HBr molecules would form 1 + 1 or 2 moles of ions. It ionized in water, right? So in this case, we would say I equals 2. And Jacobus Van Hoff in lab would find that the measured colligative property over the expected value would be pretty close to 2. Not too bad, right? Let's look at weak electrolytes, which is a little tougher. All right, you remember the dreaded weak electrolytes? Okay, so this would be weak acids or weak bases. So any of those acids that are not one of those strong ones. And then the weak bases, if you remember, were ammonia and ammonia derivatives, the amines. Hey, go back and watch the electrolytes video. if you're looking at me right now going, amines, ammonia, weak bases, I didn't remember. Go back and watch it. I'm not going to take the time to redo the video now, even though I am reviewing a little bit. So these are any species that ionize in water. They do ionize in water. They react with water and form ions, cations and anions, but they don't do it to 100% like strong acids and strong bases will. Probably not even close to 100%. Right? We're going to find out later. Most of them are probably less than 5%. A lot of them less than 1%. Right? So which means when it reacts, for example, let's take acetic acid, your prototypical weak acid. When that reacts with water, right, just like a strong acid does, it'll donate its H+, right? Remember the Bronsted-Lowry concept? So you get the hydronium ion and the acetate ion, but then these can react and go back. So you get those reversible arrows, right? You get the back and forth going on. And we'll talk about equilibrium in a later chapter. So I do get some hydronium ions and some acetate ions, but hardly any. This is the main species right here, the reacting species. These are the predominant species for weak So dominant. So remember when we do like complete and net ionic equations, any weak acid or weak base we write as the original molecule because that's by far the dominant species. But you do have a few ions, which means it's not electrolyte. So I has to be larger than 1 because you're going to get, if I put 1 mole of acetic acid in solution, I'm going to get more than 1 mole of particles, right? I'm going to get some hydronium, some acetate, and some of those. It's going to be a mixture of them. But it doesn't go to 100%, so I can't call it 2 like a strong acid. So it's going to be less than 2, but greater than 1. How are you supposed to estimate it? You can't, all right? So if I give you a problem involving colligative properties on exams or quizzes, I'm probably not going to give, well, I won't say, I will not give you a weak electrolyte, a weak acid or weak base, because you can't estimate it. You don't know. If I did, I would have to provide you the value of I. I think there's one homework problem we might do where actually we use the colligative property equations that I'll be giving you in the next 4 videos, but I give you everything except for I, and you can determine what I is from that information. Or if I gave you like Van Hoff, the measured value and the expected value, you could determine I from that. But it's greater than 1, less than 2, leaning closer to 1 for most weak electrolytes, right? Because most of them will ionize probably less than 5%. Now, if you have a weak base, right? So if that was NH3, that'd be ammonia. Replace the hydrogen with some carbon-based group, in this case a methyl group. So you got methylamine, that's an amine. These are your typical weak bases, right? Well, those are opposite. Those are going to take H+, right? Says the Bronsted-Lowry concept. So you get CH3NH3 with a positive charge, and boom, you rip that off, you get the OH-. That's why it's a base. From the Arrhenius concept, things that form the OH- in solution are bases, things that form hydronium are acids. Bronsted-Lowry, acids are proton donors, bases are proton takers. So again, that happens to probably less than 5% extent, so you're going to have some of these cations, some of those anions, and the majority of these molecules less. So I will be greater than 1. But it's going to be less than 2. See that? So we can't estimate it. So again, I will have to provide you those values. So I think I'll take a minute to talk about why we don't get exact values like for strong electrolytes, like sodium chloride, you'd expect I to be 2. It's really a little bit less than 2. It depends on the concentration of the solution, depends on the charges of the cations and anions. But there's this concept where some of those ions like to pair up, and it doesn't quite give us the nice perfect Van Hoff factors we expected. All right, one thing we're not going to count for when we do our calculations later, but I want you to be aware of. Remember, reality isn't always as nice as what we cover in class. The farther you go as a chemistry major, the more ugly doors you open up and go, whoa, that was really oversimplified in that class earlier, right? So if you take physical chemistry or PChem, you'll be realizing, wow, we make some generalities here in general chemistry. For electrolytes, mainly we're going to talk about strong electrolytes, but we could apply this to weak electrolytes as well. The predicted value based on Svante Arrhenius's theory of electrolytic dissolution, what we predicted for I, like we did before, is actually larger than what it truly is in reality. Oh man, why does that have to be so complicated? For example, if we took sodium chloride, strong electrolyte, soluble in a compound, splits 1 mole of that, splits into 1 mole of sodium ions, 1 mole of chloride ions. So we would expect or predict the Van Hoff factor to be 2, exactly 2, 100% ionization, right? But if you go into a laboratory and you take a fairly dilute 0.010 molar solution, the Van Hoff factor is actually 1.94. It's close to 2, but it's not quite. And we find that the more concentrated it gets, the lower that gets, the further from 2 it goes. So there's something funky about if there's more solute particles, there's some process going on that interferes with those ions moving around independently of each other. And so the more concentrated it is, the further this falls from 2, or whatever the expected value would be. Like I said, magnesium, chloride would be 3. We would expect it, but it's actually a little bit less than that. There's another factor. It turns out the higher the charges, right? If it's a +3 cation versus a +1, or a -2 anion versus a -1, it also deviates a bit further from what you would have expected or predicted. Why? Why? Oh man. Okay, let's take a little tiny look at it just to give you a basic idea. But I'm not going to go into gory depth on this because we're not going to be accounting for this in this class when we do the calculations. Whew. All right, I'm going to do a real major oversimplification of this. I just want you to get the concept of why that discrepancy is there for the Van Hoff factor. But again, we're just, when we do our class, we're just going to assume, like for a strong electrolyte, 100%, we're not going to worry about this factor and give integer values for strong electrolytes. I is 2, I is 3, I is 4. But in reality, if you're going to higher level work, the value is going to be a little bit less than you thought. And that's because of interionic attraction. Sometimes you'll hear the term ion pairing as well. So this decrease in the expected value of I, and we did, like I said, for the sodium chloride, it was like 1.9 something versus 2. Why is that? Well, take a look in solution here. Normally we look at like the anion with a bunch of water molecules around it with the hydrogens facing it. And we look at the cations with a bunch of waters around it with the oxygen facing it because of those dipole-induced dipole attractive forces. But if you're a large anion moving around in solution, you got all these, it's like a big, you ever see in the ocean those like big fish, like sharks and stuff, with all the little fish falling in. Blah, blah, blah. Those little fish are like the water molecules, right? So you got this big anion moving around, woo, like a chloride ion, wumba wumba. I don't know why I said wumba wumba, but anyway, apparently that's the sound of a chloride ion moving around in water. You got all these water molecules surrounding it like a sphere. But if it gets close to some of these cations, sodium ions, whatever they are, right, rubidium ions, there's still electrostatic attraction. Not enough to get it to precipitate out, but wouldn't you agree that the negative, electric field around that anion is going to that the cations are going to want to stay closer to the chloride ion, right? So they kind of cluster around it. They form these little clusters. And so that anion and those cations aren't quite as independently acting as you would think. We tend to think of them, right, as 100% independent of each other. Sodium ions are moving around. They don't even notice chloride ions, doopy, doopy, doopy. So you get a Van Hoff factor of 2 for sodium chloride. But in reality, there's going to be some clustering effect, and they don't quite act as independently as we thought. So we're going to look at a term called activity later in a separate video. So we're going to look at molarity versus activity, and activity takes into account this effect right here. So it actually, the concentration is not quite what you think it would be because of that effect. So activity, we're going to quantitatively look at this effect of interionic attractions impacting some of these properties. But the effect of this clustering is it lowers the I value from what you thought. So on the next board, I'm going to talk about the 2 factors that really influence that. Hopefully that makes sense. We can cover it right now. Wouldn't it make sense that the more of those there are, the more likely they're going to be closer to each other as the concentration gets higher, right? They're more likely to cluster together just because they're more densely packed in solution. And then wouldn't you agree that if that was a -2 charge, wouldn't these cations be more electrostatically attracted? They're going to be more likely to cluster around it. Or if those are +3s, hopefully that makes logical sense. So we'll list that up. We'll be done with this Van Hoff video, Van Hoff factor video. We couldn't do one video on Jacobus Van Hoff with all the stuff he did in kinetics and equilibrium and organic chemistry. Holy moly, well deserved for that first Nobel Prize in chemistry back, I think, in 1901. Amazing. Let's polish off this video. And again, this video applies to the next 4 when we look at vapor pressure lowering, boiling point elevation, freezing point depression, and osmosis/osmotic pressure. We're going to have to account for this. So always be thinking, what's my solute? What's my solute? Is it a non-electrolyte or is it an electrolyte? If it's a non-electrolyte, I = 1. Don't have to worry about it. If it's an electrolyte, what's I? All right, so this interionic attraction, ion pairing, ion clustering, whatever you want to call it, this is increased by, and therefore the I value decreases more due to it, right? The more interionic attractions there are, the lower the I value because the less independent those ions are of each other. Like I said, increase in concentration. There's more solute particles. They're closer together, more likely going to be attracted to each other. Like I said, a 0.5 molar solution versus a 0.01 molar solution, that I value is going to be, it's going to lower, lower, lower as the concentration gets higher and higher, higher, because there's more ion clustering, right? And then if you increase the charge, hopefully that makes sense, like aluminum's +3, sodium's +1 in solution. So obviously anions are going to be way more interested in hanging out and clustering around aluminum ion than it is a sodium ion. Makes sense? So the I value would be lower than you'd think for like an aluminum nitrate solution than it would be for a sodium nitrate solution. Right, Tab? Increased electrostatic attractions. We've got the Van Hoff factor down. Now let's start looking at some of these specific colligative properties, get you some equations for ideal solutions, super dilute, right? We're making those assumptions and we can apply some of these quantitative equations to it. Let's do it.